Hello. In this movie, we'll continue our discussion about continuous random variables. We consider real-valued random variables in this section. That is, we consider target spaces that are intervals of the real line. We'll begin with a definition. A function f from Rd to R is called a probability density function if for every vector x in Rd, f of x is greater or equal to 0, and f is integral, and the integral over Rd of f of x dx is equal to 1. For probability mass functions of discrete random variables, this integral can be replaced with a sum. We can observe also that really any function f that's greater or equal to 0, that's integrable, and whose integral is 1, can be a probability density function. We associate a random variable x with this function by p of a less or equal to x less or equal to b equals the integral from a to b of f of x dx. Here a and b are real numbers and x is a real number. This is called the law for the distribution of the random variable x. If we instead want to look at x as a d-dimensional vector of real numbers, we would consider that situation analogously. In contrast to discrete random variables, the probability of a continuous random variable x taking on a singular particular value, little x, is 0. This is because it's sort of like taking the integral from a to a of f of x dx. It's a set that has measure 0. A cumulative distribution function of a multivariate real-valued random variable x with states x in Rd is given by capital F sub x of x equals p of x1 less or equal to little x1 all the way to xd less or equal to little xd, where x is a vector of capital X is a vector of random variables and little x is a vector of real numbers. The right-hand side represents the probability that the random variable xi takes a value smaller or equal to little xi. Cumulative density function also can be represented as an integral of the probability density function f of x, so that capital F sub capital X of little x is equal to the integral from negative infinity to x1, etc., negative infinity to xd of f of z1, z2 all the way to zd, dz1, dz2, dz3 all the way to dzd. So we want to reiterate at this point that there are in fact two distinct concepts that we're talking about when we speak about distributions. First, the idea of a probability density function, our f of x, which is non-negative and sums to 1. The second is the law of the random variable x. That is the association of the random variable x with the probability density function f of x. Recall that probabilities are positive and the total probability sums to 1. For discrete random variables, this implies that the probability of each state must lie on the interval 0, 1. However, for continuous random variables, the normalization does not imply that the value of the density is less than or equal to 1 for every value. We're going to try and show that in an example. In this example, we consider two different distributions. On the left, we have a uniform distribution for a discrete random variable z. We've got three different states, z equals negative 1.1, z equals 0.3, and z equals 1.5. Because the total probability needs to sum to 1, the probability of each of these states being uniform we have as 1/3. Now on the right, we've got a uniform distribution for a continuous random variable. Is the total area of the rectangle to be equal to 1. So because our x-axis goes from 0.9 to 1.6, we know that we're going to have to go higher than 1 in order to get that rectangle to have total area 1. So in this example, our total area is 1, but the height of the density is greater than 1. Here we want to review just for a second some of the language associated with discrete and continuous probabilities. For a discrete random variable, we talk about a probability mass function when we talk about point probability, right? So the probability that capital X equals little x. For a continuous probability distribution, we talk about probability density functions, or P of X. We talk about interval probability. There really is no good way to talk about interval probability for discrete random variables. For continuous random variables, we talk about a cumulative distribution function, or the probability that x is less or equal to little x. In the next video, we'll talk a little bit about the sum mode product rule and Bayes' theorem.